Across forests, orchards, and tea gardens, plants quietly manufacture countless tannin molecules. These molecules gather in bark, leaves, fruit skins, seeds, and oak galls. To the human tongue, tannins can feel dry, bitter, and strangely tightening. To a plant, they are part warning signal, part chemical shield against grazers. They discourage hungry mouths and slow decay around wounded living tissue. For human hands, tannins became color, remedy, ink, and leather. Oak galls once helped make black ink for letters and ledgers. Bark-soaked hides became durable leather for boots, saddles, and harness. Yet the same abundance also created a stubborn biological problem for digestion and craft. Tannins cling to proteins, cloud liquids, and resist ordinary breakdown in vats and streams. In tea, wine, and fruit, their strength can become haze after cooling or storage. In fallen leaves, their grip can lock useful carbon away for seasons. The old question was simple: who could open tannins gently, without smoke or fire? Long before science answered, the forest floor was already at work. Rain softened leaves while hidden filaments moved through their brown veins. Molds and soil microbes flourished where tannins seemed chemically defensive all around fallen harvests. Nature had evolved a small key for a difficult molecular lock. That key would later receive the plain, memorable name Tannase from biologists. Its labor was invisible, but its consequences spread through every woodland. Bitter plant defenses slowly became soil, nourishment, and new growth in the cycle. The human trail began with 18th-century fascination for galls and bark. Chemists studied their acids, their dark reactions, and their affinity for hide. Gallic acid and tannic acid entered notebooks, pharmacies, and dye houses. Still, the living cause of tannin breakdown remained largely hidden inside damp cultures. In 1867, Philippe Edouard Léon van Thiam watched molds on tannin-rich matter. He observed fungi transforming tannins into simpler, more familiar substances in their flasks. Aspergillus and Penicillium appeared among organisms capable of this change through patient culture. The lesson was quiet but profound: contamination could also be biochemistry. Mold was not merely spoiling the sample, it was doing work. By the early 1900s, Albert Fernbach pursued that work deliberately for useful production. At the Institut Pasteur, fungal fermentation offered a route to Gallic acid. Tannase entered industrial history through observation, culture vessels, and patient control. Gallic acid mattered for dyes, photography, inks, and later protective chemistry. A forest defense molecule became raw material for human invention and daily craft. The name Tannase gathered around this tannin-splitting activity over time in scientific language. Researchers then found the enzyme in fungi, bacteria, and yeasts across continents. Each finding widened the map from old bark to living laboratories. The story also returned again and again to humble Aspergillus molds. Under the microscope, Tannase seems less like force than persuasion at close range. It does not burn tannins or tear them apart violently like heat or caustic chemicals. It recognizes delicate joining points inside hydrolyzable tannin molecules with careful fit. There, water helps the enzyme open bonds, patiently, one after another. Large packering structures become smaller fragments, often including gallic acid. The liquid around them may clear, soften, or change its possibilities. Nothing about the motion is dramatic at the scale of sight. Yet a drink may brighten, and a plant residue may become useful. In tea, Tannase can help reduce stubborn cloudiness after cooling in prepared extracts. Clearer infusion is one reason it became important for instant tea. In fruit juices, it can soften astringency while supporting natural clarity. In wine, it helps guide tannin balance with a measured touch. In coffee-related work, it can influence bitterness and aroma-forming compounds. These changes are valued because familiar flavors can remain recognizable after processing. Beyond the cup and cellar, Tannase connects agriculture with useful plant chemistry. It helps release gallic acid from tannin-rich leaves, pods, and residues. That molecule supports food protection, fine chemistry, and many useful derivatives. In tannery waste streams, Tannase suggests a gentler route toward cleanup. It can help reduce tannin burdens before water carries them onward. In feed research, Tannase lowers barriers in certain tannin-rich plants for nutrition studies. The purpose is not force, but access to hidden nourishment. In composting and biomass studies, it helps stubborn plant matter soften. Across these uses, the enzyme's elegance lies in its selectivity rather than brute strength. It changes a precise bond while leaving much else untouched in a crowded mixture. That precision feels modern, yet it comes from ancient ecological patience. Enzymes are industrial tools borrowed from forests, fruits, and soil for quieter factories. Tannase began as a clue in moldy, tannin-darkened plant matter. It grew into a bridge between old tanning crafts and green chemistry. Its history reminds us that industry can learn from decay. What nature uses quietly, people can adapt with care and restraint. The future may hold cleaner streams and fuller use of harvests. In Tannase, waste becomes possibility, and chemistry leans toward renewal for coming generations. Behind Enzymes Bio is a team of scientists who love this quiet biology. We gather enzymes from across the world so researchers and businesses can order from one home. Nature's technology for a greener tomorrow. See more at enzymes.bio.